Okay, good afternoon. This live stream, I'm going to be going over the June 2022 Physics Regents. So, hopefully, those of you guys that watch this find this interesting. Um, when this gets saved to YouTube, you can just like skip ahead, I guess, to the parts that you want to review. So, I'm going to be going over every question and also kind of explain some of the stuff going on. So, the physics behind each question. So, the Physics Regents this year for 2023 is this Thursday on the 22nd. Um, and what I tell my students is there's like 50 multiple choice questions and the rest is short answer. So, I'm not sure what the curve is going to be like this year, but these are the things that you're going to be given on the Regents: a scientific or graphing calculator, ruler or straight edge, a protractor, and then the 2006 edition of the reference table. So let's start. The first question says, what is basically what a scalar quantity is? It says, which terms identify two scalar quantities? So, first thing that I need to know about this question is that scalar quantities are values with magnitude only. And magnitude, this word magnitude, means size or amount. So this is not allowed to have any direction. Scalar quantities can be negative or positive, they just can't have directions associated with them. If there's a direction associated with a measurement, it's called a vector. So vectors have magnitude and direction within their values. So let's look at these choices here. We have choice 1 says force and acceleration, choice 2 says impulse and distance, choice 3 says mass and velocity, and choice 4 says energy and time. So two scalar quantities, meaning both of these quantities need to be scalars, so magnitude only. I know that force has direction, and so does acceleration. Acceleration can be east, forces can be south, or forward or backwards. Velocity is also the same thing. So that eliminates choice 3 and choice 2. Choice 3 and choice 1. So for choice 2 and choice 4, I know distance is a scalar quantity, and I know time is a scalar quantity. The answer choice here is 4. Choice 4, energy and time are both scalar quantities. Impulse has direction, so that makes it a vector. It can have direction. All right, that's number 1. So for number 2 says a motorcyclist initially traveling east at 15 meters per second accelerates uniformly at a rate of 3 meters per second squared east to a velocity of 21 meters per second east. How far does the motorcyclist travel while accelerating? And then I see my answer choices are in meters. It's a good tip to look at what your answer choices are in. So it kind of indicates what you're solving for. I see meters, so I know that it's distance. Also, this how far means distance. So distance is my unknown. So I'm going to write that down. That's what I'm solving for. There's a whole bunch of other variables that are given here. It says initially traveling east at 15 meters per second. Initially traveling east at 15 meters per second means that the initial velocity is 15 meters per second. I'm going to put east here, and I'll explain why in a second. Then it says the motorcyclist accelerates uniformly at a rate of 3 meters per second squared east. So that is my acceleration. Acceleration is 3 meters per second squared east as well. And then it says to a velocity of 21 meters per second east. So everything is east here. This actually makes it pretty simple. So this is my final velocity, which is 21 meters per second east. Now, when there's direction involved and the question doesn't say like what's the magnitude or whatever, you have to take into consideration the direction, especially with the formula that we're going to be using. So since east is kind of this way and west is this way, we're going to say that east is our positive direction, and therefore west, since it's opposite, will be our negative direction. So we can convert all of these values, 15 meters per second east to just positive 15 meters per second. Drop the east. 3 meters per second squared east, we drop the east and we can say positive 3 meters per second squared. And 21 meters per second east would be positive 21 meters per second. So we can get rid of these east and just add a positive. Obviously, if the question had other directions, you'd indicate if they were positive or negative for the calculation. Now for this problem, off the top of my head, I might not know what formula I want to use. So I'm going to bring up my reference table. Here's the reference table. And I'm going to scroll down to page 6. That's the last page. Page 6 here has the mechanics and energy and momentum formulas that are present. So I'm looking on my reference table for these variables. I'm looking for D, VI, A, and VF. So that happens to be this formula here. Let me just highlight it. This one. So I'm going to write that down. I'm going to write down VF squared equals VI squared plus 2AD. And since I'm solving for distance, what I'm going to do is I'm just going to rearrange the formula. So I tell my students that it's better to rearrange the formula first before substituting values to eliminate any math errors. So I need to solve for D here. So I have this whole term I want to move to the other side. So VI squared I'm going to subtract on this side, and I'm going to subtract VI squared on this side. This cancels out. On the left side, I'm left with VF squared minus VI squared equals, and then 2AD comes down, so 2AD. And then in order to get D by itself, I can just divide by 2A. That cancels the 2A at the top and the bottom. And I'm going to do the same thing to the left side of the equation. So this whole left side gets divided by 2A. I'm going to be left with D equals VF squared minus VI squared divided by 2A. Okay, so that's my formula I'm going to substitute. I'm going to substitute all these values in here. Now, because this is a multiple choice question, this question has a lot of work that we're doing for it. You don't need to show any work for that on the Regents. You need to just bubble in your answer sheet. But I'm going to show all the substitution here. So VF squared is going to be 21 meters per second. This whole number is squared. Minus VI, that's 15 meters per second. That whole number is squared. And then I'm dividing the whole thing by 2 times 3 meters per second squared. So 3 meters per second. And only the seconds here is squared. Okay. So now I need to put this in my calculator because I can't do that type of math in my head. So I'm going to do the numerator first. So 21 squared minus 15 squared. That gives me 216. 216 is my numerator. There's some units here. The units is that. And then the denominator is just 2 times 3, which is 6. Okay, so I'm going to do 216 divided by 6. And that gives me 36 meters. So let's see if we have that as an answer. And that is choice 3. Okay. So with these types of problems where you have to use the reference table and substitute numbers or values or quantities as variables, be careful when you're doing your math or your algebra. Okay, so let's move on to question 3. Question 3 says a battery-powered electric motor is used to cause the wheels of a toy car to rotate. In this motor, there is a conversion of, choice 1 says mechanical energy to electrical energy. Choice 2 says electrical energy to chemical energy. Choice 3 is thermal energy to electric energy. And choice 4 is electric energy to mechanical energy. So for this type of problem, this type of energy conversion stuff, I always like to think of it as a before and after situation. So there's a before situation, and then something happens, then there's an after situation, the energy conversion. So in the before situation, the problem says that there's a battery-powered electric motor. It can't be any more clear than that. This has to do something with electric energy. Okay? And then the after situation is, it says it causes the wheels of the toy car to rotate. So wheels rotating, that has to do with some type of motion. So there's electric energy converting to motion. So immediately we can eliminate choices 1 and 3 because electric energy is not first. We said that because that there's an electric, a battery-powered electric motor, that electric energy is our first thing. So that leaves choice 2 and choice 4. Motion is related to some mechanical energy process. So in this case, the answer is choice 4, electric energy to mechanical energy. So that's the answer. All right. For number 4, it says a projectile is launched horizontally from a height of 65 meters with an initial horizontal speed of 35 meters per second. What is the projectile's horizontal speed after it has fallen 25 meters? Neglect friction. So this type of problem, that I'm just going to draw a really quick setup here. We have some type of 65 meter height. Here's our projectile. It's being launched horizontally initially, and it's going to fall something like that. So with this initial horizontal, I'll call VIX, initial VI, and X for the horizontal or X direction. Something to note when it deals with projectile motion. In the horizontal direction, velocity is constant. And that is because there is no horizontal acceleration. And the reason for there's no horizontal acceleration is because there are no horizontal forces in the X direction propelling the object horizontally. So that is all to say that velocity remains the same. So if our initial velocity is 35 meters per second, that is going to be the speed at every point along this trajectory in the horizontal direction. So it's going to be 35 meters per second there, 35 meters per second there, and when it hits the ground, it'll hit the ground at 35 meters per second. So the answer here is choice 2, 35 meters per second. Let me rewrite that. All right. For question 5, question 5 says the diagram below represents two forces, F1 and F2, acting concurrently on a block sliding on a horizontal frictionless surface. And then there's a diagram. It says, which statement describes the motion of the block? Choice 1 says the block is accelerating to the right. Choice 2 says the block is accelerating to the left. Choice 3 says the block is moving to the right with constant speed. And choice 4 says the block is moving to the left with decreasing speed. So all these different answers. So here's how we approach this type of problem. So just as a hint, this is a Newton's second law problem. So we can apply Newton's second law here. We have this diagram here where there's opposing forces and they're equal. And by the way, concurrent means at the same time. Let me write that down. Concurrent means at the same time. We also have this vector here indicating that the speed of the block is to the right. The velocity of the block is to the right, actually. So if we apply Newton's second law, because we see that there's some acceleration choices here. Acceleration, according to Newton's second law, is the net force divided by mass. And in this case, the net force is the sum of all forces acting on an object. And the sum means you just add up. Okay? So if we add up these forces, we're going to have F1 plus F2. I replace F net with F1 plus F2. Furthermore, because F1 is pointing to the right and F2 is pointing to the left, one of them has to be negative since it's opposite. So let's pick F2 to be negative. So when we substitute these values in here, we're going to get F1 equals 10 newtons and F2 equals negative 10 newtons since it's opposing F1. So in this case, we just get 0 in the numerator, and 0 divided by m, we don't need to care about the mass, is 0. So the acceleration is 0 meters per second squared. So that eliminates choice 1 and 2 because it says that the block is accelerating. So it's not choice 1 or choice 2. Choice 3 and choice 4 are also different, even though they talk about speed. One is talking about constant speed, that's choice 3, and choice 4 is talking about decreasing speed. When we have a no acceleration, 0 acceleration means the speed does not change. Actually, this means the velocity doesn't change. The velocity does not change. So decreasing speed, that cannot be possible. So the answer here is choice 3. For number 6 says the magnitude of an unbalanced force applied to a 4 kilogram crate is 10 newtons. If the magnitude of this applied unbalanced force is doubled, what is the inertia of the crate? Okay, inertia is a measurement. Actually, I got that backwards. Mass is a measurement of an object's inertia. Okay, so they're basically the same thing. In taking the physics regents, you can understand that inertia equals mass. So we can say that inertia equals mass. So if we have a mass that is 4 kilograms, and it's asking for what's the inertia, and nothing's happening to the mass, then nothing is going to happen to the inertia. So the inertia is also unchanged. The mass doesn't change, so therefore the inertia doesn't change. For number 7 says a 60 kilogram man is pushing a 30 kilogram lawnmower. Compared to the magnitude of the force exerted on the lawnmower by the man, the magnitude of the force exerted by the man on the man by the lawnmower is blank. And then we have some fraction answers. 1/4 is great, 1/2 is great, the same, or twice is great. This is a spoiler alert. This is Newton's third law. And Newton's third law says for every action, there's an equal and opposite reaction. What that means is that if there is a force applied from one object, let's call it A, and it's applied on object B, that is going to be equal to the force of object B on object A. And then we add this negative sign to show that it's in opposite direction. In class, it looks like there's a table, there's a box on the table, it's at rest. The box is pushing down on the table, and the table is pushing back on the box. And then the box doesn't move because it's in equilibrium. So in this example here, we have the force of the box on the table, and that is equal to the opposite force of the table on the box. So they're just opposite in directions, but they're equal in magnitude. So in this case, the answer is the same. Since the question's asking for the magnitude of the force exerted on the man by the lawnmower is going to be equal to the same number as the lawnmower on the man. All right, that's number 7. So for number 8, I already see a circle here, so I should start thinking about centripetal motion. It says the diagram below represents a roller coaster car traveling counterclockwise in a vertical circle. When the car is in the position shown, what are the directions of the centripetal force acting on the car and the velocity of the car? And then the choices go on to say the directions for the centripetal force and the directions for the velocity. So, 2 things to know about centripetal motion is that the centripetal force and, not FA, FC. So the centripetal force and the centripetal acceleration point towards the center of a circle. So the centripetal force and the centripetal acceleration both point towards the center of the circle. The reason for that is because they're dependent on one another. The other thing is that any velocity of an object points tangent to the circle. So if we have a circle here, okay, that's my circle. There's the center of my circle. Let's say we have an object at this point here. It's moving around this circle. Let's say it's moving around this way, clockwise. Okay. Whoops. That's not what I want. Whatever, that's fine. It's going around that way. So at this point, the force points to the center of the circle. And since it's moving around the circle like that, clockwise, the velocity is going to point tangent in this direction. So that's velocity. Okay. In this diagram here, we have a counterclockwise motion, and to the center of the circle would be here. So this is where the force points, and tangent to this circle would be down this way. So that is my velocity. Okay. So we're going to look for a choice that says force is pointing to the right, since the center of the circle relative to that position is to the right. So that happens to be choice 1. All right. For number 9 says an electric motor with a power rating of that many watts is used to raise an elevator weighing that many newtons at constant speed. What is the total time required for the motor to raise the elevator a vertical distance of 20 meters? And then I have 4 choices, and all of the choices are in seconds. So let's write this down. Let's write down my givens here. So I have an electric motor with a power rating of that. So that's power. equals 6.48 times 10 to the 4 watts. That's that. Is used to raise an elevator weighing, that's the weight, this many newtons. So this is my weight. I'm going to put F with a little g. Some people might use W as well, but because I have this as watts, I don't want to put weight as W. So I'm going to use FG as my weight. So this is going to be 2.8 times 10 to the 4 newtons. What is the total time required for the motor to raise the elevator a vertical distance of 20 meters? So this is distance or height. Height is also vertical distance, 20 meters. And time is my unknown. Okay. So for this, I need to go to the reference table because I don't memorize some of these formulas. So let's go to the reference table. Reference table on this page, still on page 6, is the mechanics section. Even though it mentions something about electric motor, we're talking about weight and distance. So that's mechanics. So I'm looking for capital P, power. In case I forget what these symbols mean, the indications are on the right. The definitions are there on the right. So power, there's only one equation on page 6 that includes power, and it's this one. And I'm looking for what variables I have. I have power, force, distance, and time. So here's power, here's force, distance, and time. So let me write that formula down. So power equals force times distance over time. Now, because I need to solve for time, I'm not solving for power, I'm solving for time, I want to rearrange this formula. So I'm going to cross multiply. So to solve for t, cross multiplying is the numerator on the left times the denominator on the right, and then the numerator on the right times the denominator on the left. Since this is just one variable on the left, I can put an imaginary over 1 there. So I'm going to be left with P times T equals F times D. And then to solve for T, I need to divide by P, so they cancel out. And I'm left with the formula of T equals FD over P. So force times distance divided by power. So this is what that looks like. Force is 2.80 times 10 to the 4 newtons. Distance is 20 meters. And power is 6.48 times 10 to the 4 watts. All right, so here's a tip. This is a math tip. Since I'm just multiplying and dividing everything here, there's no addition or subtraction, I can see that there's 10 to the 4 on the numerator here, and there's 10 to the 4 on the denominator. So since it's 10 to the 4 divided by 10 to the 4, they actually cancel out. So this will make my calculation that I'm going to put in my calculator just 2.8 times 20 divided by 6.48. So this avoids that mistake of using scientific notation. So let's put that in. 2.8 times 20, and then I'm dividing by 6.48. And I get an answer of 8.64. The rest of the numbers don't matter, so 8.64. And since this is time, that's seconds. So I'm going to look for here. Choice 3 has that exact answer. 8.63 seconds. All right. For number 10 says a person standing on a sidewalk hears the siren of an ambulance as it approaches, passes by, and goes away from the person. Compared to the frequency of the sound emitted by the siren, the frequency of the sound observed by the person during this event is higher only, lower only, first higher, then lower, or finally first lower, then higher. So for this question, Tasneem, this is like a software. It's called TI Smart View. You could get it from the TI website, but I don't think it's free anymore. It was free during COVID, but I don't think it's free anymore. But you can use something like Desmos if you want to use like a graphing calculator. So for this question here has to deal with a phenomenon called the Doppler effect. So for 10, this is the Doppler effect. Doppler effect. The Doppler effect is defined as an apparent shift, and instead of shift, we'll say an apparent change in frequency of a wave when its source is in motion. So ordinarily, when an object is at rest, so let's say this is at rest, here's an object, and let's say it's a speaker, and it's making sound waves, the frequency is going to be constant, okay? However, when an object starts moving, so let's say that the object is moving this way. When an object starts moving, the frequency changes according to an observer. So it's not a real change in frequency, it's just an apparent change in frequency because of the nature of waves. So let's say it's moving to the right. The frequency over here will be higher, and the frequency over here will be lower. So on this side we have a higher frequency, and on this side we have a low frequency. So if there is an observer here and this object is approaching it and then it's going to pass it, first it's going to hear a high frequency and then it's going to hear a low frequency if this whole object is moving towards it and then away from it. So in this case, we're going to have choice 3 as our answer. For number 11 says, which particles exhibit properties of waves in some experiments? Choice 1 says photons only. Choice 2 says electrons only. Choice 3 says both photons and electrons. And choice 4 says neither photons nor electrons. For number 11, this category or this topic in physics is called wave-particle duality. And what this says is some particles act like waves. So for example, particles can collide, right, and transfer energy from one to another. And waves have like 8 different phenomena that they can exhibit. One of them is like interfering. So this is something to just kind of know, and it's based on this experiment called the double slit experiment. When you guys are doing your studies, you can look this up. This is what discovered that particles act like waves, and that's both photons and electrons. So those are some of the particles that will act like waves. All right. For number 12 says the direction of the electric field at a point in space is defined as the direction of the force exerted by the field on a 1 test mass located at that point. Choice 2 says magnetic north pole located at that point. Choice 3 says negative test charge located at that point. And choice 4 says positive test charge located at that point. So when it comes to this is also based on just something you have to know. This is based on some experiment in the past where they had some charged object and it was unknown. They didn't know what the charge of Q was. They wanted to know if it was positive or negative or something. And so what happened was they decided to choose a positive particle and place it near this object and see what would happen to the positive particle. So this object pushed it away. And then they moved the positive test particle over here, and they see that this charged object pushed it away. And then they moved it over here, and they see that it pushed it away. And everywhere they moved it, it kept pushing it away. So they concluded that this object here must be positively charged, and they were able to map electric fields and how electric fields for positive objects go outwards, and for negative objects, the electric field lines go inwards. So the answer here is choice 4. Choice 1 doesn't make any sense because electric fields and electric forces don't depend really on the mass. They depend on the charge of the object. And then the other choices are just wrong, choice 2 and choice 3. So answer here is choice 4, positive test charge located at a point. All right, for number 13 says a net force of 1 Newton will accelerate a 1 kilogram mass at 1 meter per second squared, accelerate a 1 kilogram mass at 9.8 meters per second squared, lift a 1 kilogram mass vertically at a constant speed of 1 meter per second, or lift a 1 kilogram mass vertically at a constant speed of 9.8 meters per second. So for this, if we're talking about a net force and it's equal 1 Newton, we can use Newton's second law, slightly arranged. F net equals mass times acceleration. And so if this side equals 1 Newton, we need to figure out what times what will also equal 1. Well, if we look at these answer choices here, we'll see this first one. If we plug in 1 kilogram for the mass and 1 meter per second squared for the acceleration, 1 times 1 equals 1. So that is choice 1. The other ones don't really allow a net force of 1 Newton. For number 14 says the elongation of a spring will be quadrupled if the magnitude of the force elongating the spring is quartered, halved, doubled, or quadrupled. For number 14, we need to know that quadrupled means 4 times as much, so it's 4 times greater. And also elongation means stretch. So this is a spring that's being stretched. So let me refresh my memory on what the formula is for springs stretching. That is this formula right here. Force on a spring equals K times X. So let's write that down. Force on a spring equals K, which is the spring constant, times X. So I need this formula because this is actually a proportion problem. So what I'm going to do is I'm going to rewrite K, I'm going to rewrite Fs, and I'll write X in parentheses like this. And the reason why is because the problem says that the elongation of the spring will be quadrupled. That means that X is being times or multiplied by 4. So now there's a coefficient of 4 on the right side of my equation. In math, if we do something to one side of an equation, we must do the same thing to the left side or the other side of the equation. So in this case, if we multiply the right side by 4, we have to multiply the left side by 4. Since F is the only variable on the left side, we can conclude that the force elongating the spring is also quadrupled. All right. For number 15 says the vector diagram below represents the path and distances run by a student in a cross-country race. And then we have a diagram. This student starts here. They go some kilometers this way, then south, and then east, and then south, and then west to a finish line. Question says the displacement of the student from start to finish is, and then if I look at my answer choices, I see that everything has some unit of kilometers as well as a direction north-south, north-south. So usually kilometers is a unit that you would want to convert to meters. However, since the answer choices are in kilometers, we don't need to do any type of conversions. So we're going to write down number 15. And I'm going to crudely recreate that drawing. So we have a start here. It goes this way, then it goes this way, then it goes this way, and then all the way back here. Okay, and there's my finish line. So this is 0.80, this is 0.80, this is 1 kilometer, this is 0.60, and then this is 1.80 kilometers. And then we have this nice little compass over here to indicate our direction. So if this is our starting point up here and we end up down here, our displacement, since that's what the question is asking for, is going to be a straight line path from start to finish. That's what displacement is defined as. Displacement is a straight line path from point A to point B. So we'll just say from A to B. In this case, our starting point is point A and our finish point is point B. So all we need to do is figure out what this length of this line is, and we can use the rest of the diagram to figure that out. So we can see that this section here corresponds to this number. So this is 0.80 kilometers. And this section here corresponds to this number, which is 0.60 kilometers. So we're using a little bit of geometry to figure this out. So our displacement is going to be 0.80 kilometers plus 0.60 kilometers. This equals 1.440 kilometers. Now, since we started up at one point up here, and then we did all these like east, west, south movements, we ended up, our final position relative to our starting position is actually south of our starting position. So our final position relative to our initial position is south. So in this case, we choose choice 2 as our answer. Let's move on to number 16. Number 16 says the diagram below shows the arrangement of 3 charged hollow metal spheres, A, B, and C. The arrows indicate the direction of the electric forces acting between the spheres. What spheres have static charges of the same sign? So since we're talking about charges, the two things we need to know about charges or electrostatic forces. Electrostatic forces is that like charges will repel. So that's like 2 negative charges, or an electron and an electron, or a negative 4 coulomb and a negative 1 coulomb. They will repel. Opposite charges will attract. And so that's an example of, let's say it was negative 4 coulomb and positive 1 coulomb. Those charges will attract. Or a electron and a positron. Okay? So we are looking for, and what we mean by repel means that the arrows are pointing in opposite direction. And what we mean by attract is that the arrows are pointing in like towards each other. So we're going to look for that to be the case. A and B have an attraction, so they are oppositely charged. B and C have an attraction, so they're oppositely charged. A and C are the only ones that repel. So therefore, these must be the same sign. So we're going to say A and C only, which is choice 2. All right, number 17 says 2 small charged spheres are located distance d from each other and experience an electrostatic force of attraction Fe. If the magnitude of charge of each sphere is tripled and the electrostatic force is unchanged, what other change must have occurred? So for number 17, this is another proportion problem, and I'm going to go to my reference table so that way I can find this formula that we need, which is going to be on page 4 for our electricity. So this is page 4. Under electricity, we're going to see, hold on. Okay, yeah. Under electricity, we're going to see that force equals K Q1 Q2 over R squared. And what we're going to use for this is we're going to do something similar to what we did with, what question was that? Question 14. We're going to see when we change one variable or a few variables, what happens to the other variables. In this case, the question is saying that Fe is unchanged. So that means since there's a invisible 1 in front of this force, whatever we do to the right side there, the numerator and the denominator need to be equal, so that way they cancel out and equal 1 on that side. So that way the force is unchanged. So we see that, what does it say? So it says the magnitude of the charge of each sphere is tripled. So that means that we have the magnitude of charge 1 and the magnitude of charge 2, both tripled, and the denominator, I'm going to be r squared. Technically, it's d, should be d squared since that's the variable used in the problem, but I'll just keep it as r. So just to simplify this, this is going to be 9, 3 times 3 is 9, times k times q1 times q2 over r squared. Okay, so there's a 9 on the numerator here. And remember, we need to do something to maintain that the left side doesn't change. We don't actually want to multiply by 9 on the left side. So the only other way to get rid of this 9 is to have a 9 on the denominator like this, because 9 divided by 9 will equal 1. But in order for that to happen, there needs to be our distance 3 times as well, because this square gets distributed, so 3r squared equals, so this gets distributed and this gets distributed. So this is 9r squared. So this would make it so our left and right side are kind of balanced out. So in this case, what we would do is that the distance was increased by a factor of 3. Distance was increased by a factor of 3, since that's what we did here. Okay, that's number 17. For number 18. Number 18 says, compared to the resistance of an aluminum wire at 20 degrees Celsius, the resistance of a tungsten wire of, oh, whoops, I forgot to get rid of the reference table. So that's choice 3 for number 17, sorry. For number 18, it says, compared to the resistance of an aluminum wire at 20 degrees Celsius, the resistance of a tungsten wire of the same length and diameter at 20 degrees Celsius is approximately the same, twice as great, 1/2 as great, or 4 times as great. So we're talking about an aluminum wire and a tungsten wire. So, and then this 20 degrees Celsius thing actually has to do with the reference table. So let's bring this back up. Aluminum and tungsten are on this page 4, the same page as electricity, the resistivities at 20 degrees Celsius. And we see aluminum here, and we see tungsten here. So I'm going to write those values down. So we have the resistivity of aluminum equals 2.82 times 10 to the negative 8. Units are that. And the resistivity of tungsten is 5.60 times 10 to the negative 8. Units are that. Okay, so the other formula that we might maybe need is this formula, that resistance equals resistivity times length divided by cross-sectional area. Now, since the length and the area are the same, and the only thing changing is this variable right here. That's the only thing that's changing. It's 2.82, and then the rest of that, and then 5.6, and then the rest of that. It says compared to the resistance of aluminum, the resistance of tungsten is approximately what? So something I can see here is that these values aren't that different except for the coefficients, right? So 10 to the negative 8 and 10 to the negative 8, and then ohm meters and ohm meters. So what I can do here is just compare these two values. I can use the calculator actually to come up with that comparison. So if I take 5.6 and I divided it by 2.82, those are the coefficients I'm dividing by, I get some number which is 1.98. So this is if I were to take the resistivity of tungsten and divide it by the resistivity of aluminum, I get this number, which is approximately 2. So that's the comparison, right? Tungsten to aluminum, since that's what it's asking for. It's asking for a comparison of tungsten to aluminum. So the answer here is going to be twice as great, since that's close to 2. All right, for number 19 says how much energy is expended when a current of 5 amperes is in a 5 ohm resistor for 5 seconds. So let's write down these variables. How much energy is expended? So energy when dealing with mechanics is E, but when dealing with electricity and electrostatics, it's usually W, okay, for the work. So this might be what we're solving for. Let me put that down. Maybe it's what we're solving for. It says when a current of 5 amperes, so 5 amperes, is in a 5 ohm resistor, so 5 ohms, for 5 seconds. That's my time. So 5 seconds. So everything is 5 here. I'm gonna, I forgot to take off the calculator. So this is question 19. So for this equation from the reference table, I'm looking for work, I'm looking for current, I'm looking for resistance, and I'm looking for time. And that happens to be this formula right here: work, current, resistance, and time. So let me write that down. So work equals current squared times resistance times time. So I'm solving for this, so I can just multiply everything. So this is going to be 5 amperes squared times 5 ohms times 5 seconds. So 5 times 5 times 5 times 5. This is 5 to the 4th power, which is 625 joules. Well, let's write that down. 625. All right. For number 20 says the amount of electric current through an unknown resistor may be measured by connecting. So when we want to measure current, ammeters measure current. And voltmeters measure potential difference or voltage. Potential difference, voltage. Okay. Now, the ammeter must be connected in series, meaning it must be along the same branch as the thing it wants to measure. And voltmeters must be connected parallel or in parallel to the thing it wants to measure. That means you need to create a new branch. So the only thing that follows, the only choice that follows both of those rules is an ammeter in series with the resistor. So choice 1 is number 20. All right, let's move on to number 21. Number 21. Which phenomenon represents a wave spreading out behind a barrier as the wave passes by the edge of the barrier? So what this represents is diffraction. Okay? And the other ones don't really fall into that definition, so you can answer this with the process of elimination. Reflection is when the wave reverses direction. Interference is when two waves add or subtract. And refraction is when the wave changes speeds. So diffraction is the only one by process of elimination that bends. And the whole thing is you have a barrier here with some type of opening. This is the edge of the barrier that they're talking about. And you have these waves coming in, and these waves will hit this, and then as they get through this barrier, they will bend around the barrier. Kind of, I like to think about it like squeezing through. All right, for number 22. 22 is a 1 kilometer length of copper wire A with a cross-sectional area of that meter squared. It has a resistance of 0.172 ohm at 20 degrees Celsius. Another copper wire B is half as long and twice the cross-sectional area of wire A. What is the resistance of copper wire B at 20 degrees? Okay, so that formula that we just borrowed, we used here, this one, it seems like we might need to use it here. So I'm going to rewrite that. That is resistance equals resistivity times length divided by area. Now, so this is wire A, not to be confused with the area. So wire A and wire B. Okay, so they're both copper. Okay, wire A is 1 kilometer in length. So length equals 1 kilometer. This is 1,000 meters. All right, that's something we need to convert. And it says it has a cross-sectional area. So area of 1 times 10 to the negative 4 square meters. And it has a resistance of 0.172 ohms. Okay. Now, it says that wire B is half as long. So this is L divided by 2. Let's put that there. And it says that the area is twice. So area is 2 times the area. What is the resistance of B? Okay, so if we look at this formula, and since this number here, okay, is 0.172 ohms, we're going to use A as a basis, the first one. And what we're doing is resistance is the same, so that doesn't matter, but the length is half. So I'm going to put L over 2 instead of 500. So L over 2 is 500. And my area is 2 times the area. If I simplify this, right, this denominator here and this denominator here, this will combine. So on the numerator we'll have rho times, the length over, and on the denominator we're going to have 4, I forgot to change the color, we're going to have 4 times the area. Okay, so this 4 is just on the denominator, because this is what happens when you combine the 2 times 2, we'll have 4 on the denominator here. So if we have 0.172 ohms on the left side, and we have a 4 on the denominator on the right side, we need to divide this side also by 4. And this will give us our answer of what the resistance is. So the resistance is going to be 0.172 divided by 4. So the resistance of B is going to be the resistance of A divided by 4, which in this case is 0.172 ohms over 4. And let's see what that is in the calculator. So 0.172 divided by 4, and we get 0.043. So let me write that down. 0.043 ohms. And that answer is this choice right there. So it seems like this Regents had a lot of proportions on it. There's a lot of math involved here and not too many like crazy physics. So for number 23, number 23 says the magnitude of electric force exerted on a small positive charge located between 2 oppositely charged parallel plates is 1 smallest near the positive plate, 2 smallest near the negative plate, 3 greatest midway between the plates, 4 the same everywhere between the plates. The answer here is everywhere between the plates. So when you have 2 parallel plates, and let's say this one is positively charged, this one's negatively charged, and we have like the electric field lines that go like this. This is just a property of parallel plates. They have a uniform, this means constant, electric field, and electrostatic force in between the plates. So everywhere in between the plates is going to have the same electric field and the electric force. For number 24, number 24 says an acoustic organ is a musical instrument with pipes. The oscillation of air molecules in the pipes of the organ produces sound waves that are electromagnetic longitudinal, electromagnetic transverse, mechanical longitudinal, mechanical transverse. So sound waves are not electromagnetic. And furthermore, sound waves are longitudinal waves. So for number 24, the thing to remember is sound waves are mechanical and compression or longitudinal waves. Okay. 25 says, which list identifies portions of the electromagnetic spectrum in order of increasing frequency? So, increasing frequency. I need the reference table for this. So, let's bring up the reference table. Electromagnetic spectrum up here has, so increasing frequency means we start with radio waves, then go microwaves, so radio waves, then microwaves, then infrared, then visible light, then ultraviolet, then X-rays, then gamma rays. So if I look at these choices here, increasing frequency, I see that gamma rays are included first. Gamma rays are like the highest frequency waves, so 1 and 4 are eliminated. And then I see 2 and 3 have gamma rays at the end. So for choice 3 has infrared, visible, ultraviolet, gamma ray. If I look at the reference table, it goes infrared, visible, ultraviolet, gamma rays. So that is the answer. Okay, for number 26. Number 26 says a tuning fork is used to produce a sound wave having a frequency of 517 hertz. What is the wavelength of the sound wave in air at STP? Okay, so for this, it wants me to figure out the wavelength. It also gives me the frequency, which is 512 hertz. And for sound, if I need the speed of sound, that is on the reference table on page 1. So page 1 has the speed of sound in STP, or at standard temperature pressure. That's this right here. We see that it is 3.31 times 2 times 10 to the 2 meters per second. Let's write that down. That is 3.31 times 10 to the 2 meters per second. I'll also need to go to another page on the reference table since I don't remember this formula. So I'm going to go to page 5 of the reference table to look for a formula that has speed, frequency, and wavelength. That happens to be this first formula here on waves. This is the wave speed formula. So that is V equals frequency times wavelength. I'm going to rearrange this formula to solve for wavelength. That rearrangement looks like this. Okay, so I'm going to divide by frequency on both sides. And that gives me, that cancels out, that gives me wavelength equals velocity divided by frequency. The speed is 3.31 times 10 to the 2 meters per second, and the frequency is 512 hertz. 10 to the 2. So let's bring out my calculator. We have 3.31 times 10 to the 2. I'm going to use this shorthand notation. I'll show what it looks like when you use the scientific notation and whatnot. And divide by 512. We get that answer. Is that right? Let me just double check. Yeah, that's right. Okay. And then if I wanted to show the scientific notation, like the regular times 10 to that, that looks like 3.31 times 10 to the 2. Then what I'm going to do is I'm going to make sure that there's parentheses around this, okay? Because I don't want to mess up my calculation. When you use this, the times 10 to the exponent, make sure you put that term, that value in parentheses. Now I'm going to divide this by 512. And then I get the same answer. Sometimes when you don't use parentheses, you will not get the correct answer, so be careful with that. So that answer, 0.646 meters, is choice 1. Okay. Moving on to question 27. 27 says, an amplified sound wave produced by an opera singer shatters a glass. Which phenomenon best represents this event? With some of the other questions that we answered, we can eliminate diffraction and we can eliminate reflection. So in this case, the answer is resonance. Resonance is really associated with wine glasses and opera singing and matching frequencies. So in this case, resonance is vibrating objects or particles at a certain frequency that causes nearby particles to also vibrate. And then what happens is all these vibrations add up. So you get a huge amplitude, a lot of energy happening, and then that's when the wine glass shatters. So that's resonance. All right, for 28 says the diagram below represents a wave traveling in a rope in the direction indicated. Which arrow represents the motion of a particle at point P at the instant shown? So this is a transverse wave, and transverse waves have perpendicular motion. Transverse waves. So we have perpendicular motion relative to the motion of the wave. So the motion of the particles are perpendicular to the motion of the wave. So if the wave is moving to the right, as indicated in this problem, the particles will oscillate up and down. So that eliminates choice 1 and choice 3. In this case here, if we have a wave, and this is the way that I like to do it, if we have a wave and it's moving to the right, I'll kind of like redraw this wave, shift it over to the right, like this. And I'm going to draw now an arrow from this point to where the new wave is. So that's up there. So that's the answer, choice 4. For number 29 says, if several resistors are connected in series in an electrical circuit, the potential difference across each resistor varies directly with the resistance of each resistor, varies inversely with the resistance of each resistor, varies inversely with the square of the resistance of each resistor, or is independent of the resistance of each resistor. Oh boy, okay, so it says it's connected in series. So the series rule for potential resistance is this, potential difference is this right here, that they add up, okay? So they add up. So I'll come back to that. The other thing that we'll need here is Ohm's law, because it's talking about resistance and the potential difference. So that's the other thing we'll need. So let me write those down in my space here. So first, Ohm's law. And then secondly, for series, that the voltages add up. Okay? So it's asking for if several resistors are connected in series in an electric circuit, the potential difference across each resistor. So what that looks like is you have a whole bunch of resistors connected like this, okay, in series. So it wants to know what's the potential difference of that, what's the potential difference of that, what's the potential of this, and what's the potential difference of this. So in that case, let's rearrange this formula to solve for potential difference, which will be V equals IR. So that's what we're going to substitute in for each one of these V's. So V1 is going to be I1 times R1. V2 is going to be I2 times R2. And V3 is going to be I3 times R3, and so on. So what this means is the answer is choice 1. It varies directly with the resistance of each resistor. So V is directly proportional to R. And that's shown here by Ohm's law. Okay, for number 30, number 30 says, in medium X, light with a wavelength of that many meters travels at 2.20 times 10 to the 8 meters per second. In medium Y, this light has a wavelength of that. What is the speed of light in medium Y? Okay, cool. So for this question, question 30, let's write these things down. Let's say I'm going to do 1 and 2. So for medium 1, this we'll call medium Y. Medium X, sorry. And for 2, we'll call medium Y. So let's write down these variables. It says medium X, the wavelength is that. So wavelength of medium X is 3.44 times 10 to the negative 7 meters. And it travels at a speed of 2.2 times 10 to the 8 meters per second. So that's that. And then in medium Y, this light has a wavelength of that. So in medium Y, the wavelength is different. It's 3.12 times 10 to the negative 7 meters. And we don't know what the speed of light is in that medium. That's what we're going to be solving for. Okay, so for this one, what we need to do is go to our reference table. And we need to see if there's a formula that involves 2 different wavelengths and 2 different speed of light. So let's bring up the reference table. With waves, that's page 5. And the formula that we need is this one right here. But we don't need all 3 parts. We actually just need speed of light and wavelength. So let me write that down. We have a ratio V1 over V2 equals lambda 1 over lambda 2. Okay, so I called medium X 1, so we'll just put a 1 here and a 1 here, and I called medium Y 2, so we'll just put a 2 here and a 2 So we'll just do our substitution, but before we do that, let's make sure that we're solving for V2 first. So in order to do that, I'm going to cross multiply. So let's cross multiply. Okay, so we'll cross multiply. So V1 times lambda 2 is V1 times lambda 2, and V2 times lambda 1 is V2 times lambda 1. I'm solving for V2, so I'm going to divide by lambda 1 on this side. That cancels that out. Divide by lambda 1 on this side, and I'm going to be left with V2 equals V1 times lambda 2 over lambda 1. So the speed of light of medium x times the wavelength of medium y divided by the wavelength of medium x. Okay, so the substitution looks as follows. We have 2.20 times 10 to the 8 meters per second. I'll put this in parentheses. And we're multiplying by the wavelength of medium y. So we got 3.12 times 10 to the negative 7 meters. And we're dividing that by the wavelength of the wave in medium x, which is 3.44 times 10 to the negative 7 meters. Okay. Again, since we're multiplying and dividing everything, I'm going to notice here that I have 10 to the negative 7 here and a 10 to the negative 7 here. So I'm just going to cancel this out to simplify my calculations. So it gives me, what I'm going to put into my calculator is 2.20 times 10 to the 8 times 3.12, and then that whole thing is divided by 3.44. And this should give me meters per second. So let's see if we get an answer. So let's pull up this calculator. We're going to do 2.20. I'm going to do my shorthand notation. So times 10 to the 8 times 3.12. And then divide that by 3.44. I get a really, really large number. Okay, so let's see if I put it in scientific notation, if that changes anything. So parentheses 2.20 times 10 to the 8, close the parentheses, we're going to multiply by 3.12 and then divide that by 3.44. Same answer. Okay, so let me write down this whole number. We got 1,995,348,83.7. If I move this decimal over 1, 2, 3, 4, 5, 6, 7, 8, we get 1.99 times 10 to the 8, which is approximately 2 times 10 to the 8. So that ends up being our answer. After all that, answer is that. All right. For 31, it says a nuclear reactor produces this many joules of energy per year. How much mass is converted to energy by the reactor in 1 year? So it gives me energy, 2.7 times 10 to the 16 joules. How much mass is converted? Mass. So on the reference table, let's bring up the reference table. We're still on page 5. The only formula that we can use really is going to be this formula. This is the energy mass equivalence. And so what this is it means that energy can convert to mass, and mass can convert to energy. You'll notice that the formula requires the speed of light. So E equals mc squared. We need c. On page 1 of the reference table has c, which is the speed of light. That's this value. So let's write that down. Let's do the substitution. So we have, oh, actually we don't want to do that substitution yet, because we need to solve for mass. So let's solve for mass. And this is going to be a simple one. We're just dividing by c squared on both sides. So mass is equal to energy over c squared. So that looks like 2.7 times 10 to the 16 divided by 3 times 10 to the 8, and then this term is squared. So in my calculator, let's see what this looks like. We have 2.7 times 10 to the 16, and we're dividing by 3 times 10 to the 8, and 3 times 10 to the 8 is squared. So this gives me a whopping mass of 0.3 kilograms. A lot of joules of energy for a little bit of mass. This gives us answer choice 1. For 32, 32 says the diagram below shows the initial charge and position of 2 identical conducting spheres on insulating stands. If the spheres are brought into contact with each other and separated, sphere B will have a net charge of blank. And then we got a whole bunch of positive and negative values. So for 32, when conduction occurs, conduction is you're going to have the charge of the first object plus the charge of the second object, and it's divided by 2. And this is going to be the charge on each new object. So that's going to be negative 7 times 10 to the negative 6 coulombs plus 3 times 10 to the negative 6 coulombs divided by 2. And let's put this in the calculator. We'll have negative 7 times 10 to the negative 6 plus 3 times 10 to the negative 6, and this whole thing is divided by 2. We end up with an answer of negative 2 times 10 to the negative 6 coulombs. So something to note with the calculator is this button here means minus subtraction, and this button here means negation, so negative. So you use this when you want to put a negative sign in front of a number, and you use this button when you want to subtract 2 values. So just be careful, because sometimes you'll get errors if you switch the 2. Alright, so in this case the answer is choice 2. For number 33, number 33 says an anti-muon neutrino is, okay, let's write this down. Anti-muon neutrino. Let's bring up my reference table. When dealing with muons and anti-muons and all that, this is page 3. So here we see there's a muon neutrino right here, and this is under lepton. So a muon neutrino is a lepton. Okay, and it has a charge of 0. 0 elementary charges. So that's the charge equals 0. For antiparticles, it has the opposite charge. So the opposite of 0 is 0. So the answer here is going to be choice 2. Lepton with a 0 charge. All right, for number 34. Number 34 has 2 waves. And we're supposed to figure out what the superposition is. So it says, the graph below shows the displacement of a certain particle in a medium versus time due to 2 periodic waves A and B traveling through the medium. The superposition of the 2 waves will cause the particle of the medium to have a maximum displacement of blank. Okay, superposition. Superposition means adding waves. This is when the waves add up. This is basically another thing for interference. Okay, I'm gonna give a little cheat here. So it's basically interference. So in this case, what we're gonna do is we want to look on the wave, and we want to see what these maximum displacements are, so we can figure out the new maximum displacement. So the maximum displacement for wave A occurs here. Whoa, not a parallelogram, which is at 2. So for A, it's 2 meters. And the maximum displacement for wave B happens at 3 meters. So the displacement for B equals 3 meters. So the new displacement is going to be A plus B. That's the superposition. That's going to be 2 meters plus 3 meters, and that's simply 5 meters. So that is choice 4. So the scary part of this question is the word superposition. For number 35. Number 35 says, the diagram below represents a wire that is not part of a complete circuit, just above the poles of 2 magnets. Moving the wire downwards between the poles in the direction shown in the diagram will 1. Induce an alternating magnetic field between the poles of the magnets. 2. Induce a potential difference between the ends of the wire. 3. Decrease the wire's resistivity. Or 4. Reverse the direction of the magnetic field. Okay, so let's do a process of elimination here. First of all, the wire's resistivity cannot change unless you change the wire. So the wire is not changing, so there's no change in the resistivity. Secondly, reversing the direction of the magnetic field. This most likely won't happen unless you change the direction of the magnets. So the magnets aren't changing, so the direction of the magnetic field shouldn't change. All right. So then we're left with 1 and 2. So 1, it says induce an alternating magnetic field between the poles of the magnets. This is also wrong, and I think this word induce might tempt some students that study these types of questions, because when you move for 35, the whole idea is electromagnetic induction, and electromagnetic induction basically has to deal with moving electric fields will create magnetic fields, and moving magnetic fields will create electric fields. That's because when you move a magnet, current will start flowing through any conductors. And when you start moving the electric fields, a magnetic field gets created. So this word induction, induce, I see that it's here, so I might be tempted, oh, that's probably the whole thing. But make sure you read the whole question and all the answer choices before making your choice. So the answer is induce a potential difference between the ends of the wire. So the potential difference means you have a low voltage here and a high voltage here potentially, or a positive voltage and a negative voltage. That is a potential difference. It's a difference of potentials. So the answer is 2. All right. So that concludes section A. Section A. A lot of multiple choice questions. Let's get through these remaining parts of the exam. So this is now part B1. This is 36. 36 says, which graph best represents the motion of an object traveling at constant positive velocity? Constant positive velocity. So, constant velocity means no acceleration. If there's no acceleration, if we look at this formula on the reference table, this one, let's copy this formula down. Okay. If there is no acceleration, this term equals 0. So we can rewrite this equation as d equals initial velocity times time. This is a function of distance or displacement as a function of time. So that means that we can graph, this is on the y-axis and t is on the x-axis, so time and displacement. If we were to graph this, we would get a nice straight curve like this, because it must be positive since the problem says positive. So the answer is that. Choice 1. Number 37. Number 37 says a cannonball is fired with an initial velocity of 100 meters per second at an angle of 15 degrees above the horizontal. What are the horizontal Vx and vertical Vy components of this velocity? So we're being asked to figure out Vx and Vy, horizontal and vertical components. Okay, the other things I'll also include is the initial velocity, which is 100 meters per second, and theta, which is 15 degrees. So let's bring up the reference table. We're looking at these two formulas here. These have to deal with vectors. These are general equations for figuring out the components of a vector. So if you have a vector that is pointing in some direction, there is going to be a horizontal component that makes up that vector, and there is going to be a vertical component that makes up that vector. So this is Vy, and this one on the horizontal is Vx. So we can use those formulas. Let's rewrite them. We have Ax equals A cosine theta, and Ay equals A sine theta. In this case, instead of A, we have V, and instead of Ax, we have Vx, and instead of Ay, we have Vy. So replacing those, we have Vx equals v cosine theta, and Vy equals V sine theta. Substitution looks as follows. Now, if I look at this, before I move forward, let's take away the reference table. If I look, before I calculate both of these, I actually need to calculate one, because I can see based on the answers, all of the Vx's are different. 96.6, 25.9, 76, and 65. So I only need to calculate Vx. And once I get my Vx, it's going to be correct. I'm going to calculate both in this case to show, but sometimes you can save time on the test. Just need to calculate one. So here, Vx is going to be equal to V, which is 100 meters per second, times cosine. Cosine is a function. 15 degrees is what we're substituting. So here's what the calculation looks like. Before I do my calculating, I want to make sure that the mode in my calculator is in degree mode. So I can see here that it's not, it's in radians. So I want to change this to degrees. You can change the mode of your calculator by clicking mode and then changing what parameters you need to change. And then you can exit out of this by clicking second mode to quit. Okay, so I'm going to do 100 times cosine of 15 degrees, and that gives me 96.59. Let's write that down. 96, I'm going to round this to 6 meters per second. So if I look here, that gives me choice 1 is the answer for Vx. If I do the math for Vy, we'll do 100 meters per second times sine of 15 degrees. And this will give me 25.9 meters per second. Tasneem, to answer your question about when do you change it, when you're taking the Physics Regents, always keep it in degree mode. So all the equations use degrees that involve sine, cosine on the reference table. You'd maybe change it back to radians if it's your own personal calculator, if you're in like an algebra class. Okay, so for 38, it says a 1,200 kilogram car is moving at 10 meters per second when a braking force of 3,000 newtons is applied. How much time is required to bring the car to rest? Okay, easy one. Let's write out our givens. We have a mass of 1,200 kilograms. It's moving at 10 meters per second. So that's our initial speed. Initial speed is 10 meters per second. When a braking force, so it's braking, so I'm going to apply a negative force here. So negative 3,000 newtons. It does not indicate that it's negative, but that word braking means that it's an opposing force. How much time is required to bring the car to rest? So bringing the car to rest means that the speed is 0 meters per second. Bring to rest means the final speed is 0. So the unknown here is time. According to our reference table, we need to combine two formulas. Okay? We need to combine this formula, the impulse formula, and our momentum formula. So let's write those down. We have, I'm going to write down the whole thing here, but F net times time equals delta P, and also P equals mass times velocity. Okay. All right, so for this, we actually don't need J. We just need this section. So let me rewrite that. We have F net times time equals delta P. Recall that delta P is equal to final momentum minus initial momentum. And if momentum equals mass times velocity, final momentum is going to be mass times final velocity. And initial momentum is going to be mass times initial velocity. Now, since final velocity is 0, this term here cancels out. So we can rewrite, and this is all that's left. So we can rewrite this formula to F net times time equals delta P is now negative mv, so negative mv1 vi. And we're solving for time, so I'm going to divide by net force on both sides. So time equals negative mvi over F net. This substitution looks like this. So 1,200 kilograms times initial velocity is 10 meters per second. And the force is negative 3,000. So let's put this into our calculator. So we have negative 1,200 times 10, and we're dividing by negative 3,000. And we get a simple 4. So t equals 4, and the answer is t equals 4 seconds. That's choice 4. All right, for number 39 says, which graph best represents the relationship between speed of light in a transparent medium and the absolute index of refraction of that medium? So for question 39, we're relating speed of light. This is, by the way, speed of light in a vacuum. Speed of light in a medium, so it represents the speed of light in a transparent medium. Speed of light in a medium is v, so this is speed of light in a medium. And n is the absolute index of refraction. Okay, let's bring up our reference table. Reference table with absolute index of refraction, that's page 5. Let's write down this formula we see here. So that is n equals c over v. We need this formula because what we need to see here on these graphs, this is our y-axis, okay, and this is our x-axis. So on a graph, this is our y-axis, this is our x-axis. We graph things with the y on the left side of the equation, and x is usually on the right side. So if we're going to graph this function y equals x, this is what the graph looks like. So we need the similar thing here. So if we see that on the graphs, the speed of light in the medium is on the y. So that's this. We need to place this as our y variable, and we need to get that over here. But n, which is actually on the x-axis, since it's the absolute index of refraction, we need to move that to the other side. So let's cross multiply this. We'll get nv equals c, and then we're going to divide by n. So dividing by n will give us v equals c over n. Okay, so now we have this in the form of y equals some constant over x. Okay, so this is the form of the graph we're looking for, which is y equals x inverse. Let me just double check that that is the correct answer. Yeah, that's the correct answer. Cool. That's choice 1. All right. For number 40, it says a student uses a string to whirl a 0.25 kilogram mass in a horizontal circular path that has a 0.80 meter radius. If the magnitude of the centripetal force exerted on the mass with the string is 25 newtons, what is the speed of the mass? So speed of the mass. Let's write out all these variables. So we have mass equals 0.25 kilograms. We have radius 0.80 meters. We have the centripetal force is 25 newtons. Centripetal force is 25 newtons. And it wants to know what the speed is. So let's see if there's any formulas that look like this. So centripetal force is on the last page of the reference table. And I'm seeing these two formulas. Both of these formulas, let's copy down. We'll have to rewrite them. So FC equals M times AC, and AC equals V squared over R. Okay, so I need to solve for V. I'm going to combine both of these formulas. So I'm going to take acceleration and substitute it into here. Okay, so this is what that looks like. It looks like FC equals M times V squared over R. That's the substitution. Now what I can do, I have a formula with all these variables, V, F, R, and M. I'm going to rearrange this to solve for V. So we're going to cross multiply. This is going to give us FC times R equals MV squared. Then I'm going to divide by M. So that's going to be FC times R over M. And then I'm going to take the square root on both sides. So taking the square root on both sides, we will get radical FC times R over M. And this is equal to our velocity. So this is the formula that I want to use as I'm substituting. So let's rewrite this formula. I'm use a different color. So V equals the square root of FC times R over M, and let's substitute, okay? So FC is 25 newtons, R is 0.80 meters, and M is 0.25 kilograms. So let's put this in the calculator. We're going to do square root of 25 times 0.80 divided by 0.25, and that gives us 8.94 meters per second. Let's see if that is a answer choice. 8.9 is close, so we'll use choice 2. Number 41 says a deuteron is formed by combining a proton and a neutron. The mass of a deuteron is 2.39 times 10 to the negative 3 universal mass units less than the combined masses of a proton and a neutron. This mass difference is equivalent to. So let's write down. It says the mass is equal to times 10 to the negative 3 universal mass units. Universal mass units. This is not kilograms. So oftentimes when you see something that you're maybe unsure of, it's a good place to go to the reference table. Let's go to page 1 of the reference table and let's see if we have anything about this universal mass unit. I see here it says 1 universal mass unit is equal to this number. So let's write that down. So 1 universal mass unit, U, is equal to 9.31 times 10 to the 2 MeV, mega electron volts. That's what that stands for. So that's what 1 universal mass unit is. So in order to figure this out, if I need to figure out what this mass difference is equivalent to, the problem is really set up with some confusing vocabulary with this whole difference. You might be thinking, oh, maybe you need to subtract something. No. All you need to do is multiply these two numbers, because this is what the mass is that you're trying to figure out and convert, and this is what 1 equals. So you need to convert this number, this universal mass unit that's in the problem, to this unit. So you just multiply the two. So you're going to do 2.39 times 10 to the negative 3 universal mass units, that's the thing. And you're going to multiply this by this number. So this is 9.31 times 10 to the 2 mega electron volts per universal mass unit, per 1. So let's put this in the calculator. You're going to get 2.39 times 10 to the negative 3 times 9.31 times 10 to the 2, and we get 2.225. Let's write that down. 2.22509, and the units are mega electron volts, since the U's will cancel out. So this is what our answer is. But if we look, 2.23 is the closest answer. So that's going to be our answer. Next, number 42. Number 42 is kind of another one designed to like trick people up. So number 42 says a gravitational force of magnitude F exists between Earth and a satellite on Earth's surface. So when it's on Earth's surface, it equals F. The satellite is sent into orbit at a distance of 3 Earth radii above Earth's surface, as shown in the diagram below. So R represents the radius of Earth, and 3R represents 3 times the Earth's radius above the surface of the Earth. What is the magnitude of the gravitational force between the Earth and the satellite when the satellite is in orbit? Okay, so we're reusing that formula that I'm sure looks familiar. This comes from page 6 of the reference table, just for reference, right here. Okay, so we're using that. And the only reason why we need to use this is for that, the relationship between F and R squared. Okay, so initially it's saying, so on the surface of the planet, F is equal to G M1 M2 over capital R squared. Okay, so we're replacing the R in the diagram with little r, and we're replacing FE with F from the problem. Okay, so that's on the surface. In orbit, this is no longer just F. Okay, so I'm going to put F, but there's some blank number that needs to go in front of this, right? You'll see in the answer choices, it's either 1 over 16, 1 over 9, 3, or F, or 4. So now what we're going to do okay, so sorry about that. So now what we're going to do is we're going to rewrite these variables, and we need to figure out what goes here. Is it 3 or something else? Well, it's something else because R is measured from the center of the planet to the surface. So 3R is measured from the surface to the orbit. So this is not the real distance. It's actually 3R plus R, which is 4R. Let's make this a different color. So this is 4R actually. So 4R squared ends up being 16 on the denominator. So that means we need to have a 16 on the denominator for our F, which gives us choice 1. Alright, 43. 43 is another one that might trip you up because you could get like 2 possible answers. So but only one is correct. This one says, as part of an investigation on quantization, a student measured and recorded the mass of 5 identical containers, each holding a different number of pennies. The table shows the student's data. Based on the data, what is the most likely mass of 1 penny? Okay, so we'll see 3.2 grams, 6.4 grams, 9.6 grams, 12.8 grams. And what we want to do here is we need to look for numbers that are similar. So this number here and this number here are similar. So let's write them down. We got 35, oops. Okay, whatever. 30, I keep putting 3.5. 35.2 grams. And we have 38.4 grams. If we subtract these two, let's see what we get in the calculator just to make sure. So 38.4 minus 35.2 gives us 3.2. Okay, so let's put 3.2. All right. Let's look at another similar value. So we got 41.6 and 48. Let's subtract those two. Okay, so let's do 48 grams minus 41.6 grams. When we do that calculation, 48 minus 41.6, we get 6.4. Alright, so which one is it? These are most likely all whole pennies, okay? And it says, based on the data, what is most likely the mass of 1 penny? So it's not possible that from container 1, right? Here's container 1, and then here's container 4. That's what we just compared in the first section. This is container 1. This is container 4. It's not possible that there's a half penny here and then a whole penny between containers 3 and containers 5. Okay? What's more likely is this value here represents 2 pennies and this value here represents 1 penny. So the answer here, just by some, I guess, like basic logic after subtracting, is choice 1. All right. For number 44, which graph represents the relationship between frequency and period? So for 44, we're trying to figure out how frequency is related to period. So if we look on the reference table, it gives us the answer. So let's look at frequency and period. Frequency and period are right here. They're inverses. So frequency and period are inverses. So the only graph that shows an inverse relationship is choice 4. For number 45 says, what is the current in a conductor if this many electrons pass a given point in the conductor in 10 seconds? So we have the number of electrons. So number of electrons equals 3.15 times 10 to the 18 electrons. We're going to use E elementary charges for electrons. And it says the time is 10 seconds. We're being asked for the current. According to the reference table, page 4 says that current is equal to the charge divided by the time. So current equals charge divided by time. However, we were not given the charge, we were given the number of electrons in elementary charges. So this here is the charge of the electron in elementary charges. So we need the charge of the electrons in coulombs. So bringing back up this reference table and going to page 1, it tells us that the elementary charge is equal to this many coulombs. So this is saying that 1 electron equals 1.60 times 10 to the negative 19 coulombs. So we have this many electrons. And that many electrons is going to be equal to that number times this number. So in the calculator, let's bring up the calculator. We're going to have 3.15 times 10 to the 18. And we're going to multiply that by 1.60 times 10 to the negative 19. And we get 0.504 coulombs. So this is the charge that we want to use. So that's what Q equals. So let's substitute that in. We get 0.504 coulombs divided by 10 seconds. If we're dividing this by 5, we just move this decimal place over. So this is going to be 0.0504 amperes. And that gives us choice 1. For number 46 says a particle with a charge of positive 3 nanocoulombs is placed in an electric field. With a magnitude of 1500 newtons per coulomb, what is the magnitude of the electrostatic force on the particle? Okay, so let's write this down. So 46, we have charge equals positive 3 nanocoulombs. Nanocoulombs needs to be converted. According to our reference table, nano is this right here. So we're going to replace nano with times 10 to the negative 9 coulombs. So that's what that equals. Next part of the problem says it's placed in an electric field with a magnitude. So the electric field has a magnitude of 1,500 newtons per coulomb. What is the magnitude of the electrostatic force? Let's go back to the reference table to figure out what formula we need to use. So we're on page 4, and we see this formula right here: electric field, charge, and electrostatic force. So let me write that down. So we have the electric field equals the electrostatic force divided by the charge. So what I want to do is I want to solve for the electrostatic force. So the electrostatic force is going to be equal to the electric field times the charge. And this looks like this. This is the substitution. So E is 1,500 newtons per coulomb, and Q is this. So 3 times 10 to the negative 9 coulombs. And in the calculator, this is what this looks like. So 1,500 times 3 to the negative 9. And we get 4.5 times 10 to the negative 6. Since this is a force, it's measured in newtons. 4.5 times 10 to the negative 6 is choice 1. All right. Almost done the multiple choice. Yay. This is a long, very long stream. Okay, 47 says, the graph below represents the motion of an airplane that starts from rest and takes off from a straight runway. Which quantity is represented by the slope on the graph? This one's a very easy one. So slope is equal to your y-axis divided by your x-axis. So on the y-axis, we have velocity. This is your y-axis. And on your x-axis, you have time. So a formula, velocity divided by time, if we check on our reference table, velocity divided by time is this formula right here. So that's acceleration. This equals acceleration. So the slope of a velocity versus time graph is equal to acceleration. For number 48. 48 says, diagram below represents two horizontal platforms that are at different heights above level ground. A ball rolls off the taller platform with a horizontal speed of 15 meters per second, travels through the air, landing on the top of the shorter platform. What is the total time the ball is in the air? Total time the ball is in the air. Solving for total time. Okay, so in order to solve this, let's use a formula on the reference table, okay? First, before we figure out what formula, we need to write down what variables we have. We have V, it says it rolls off with a horizontal speed. So, horizontal speed, this is our initial velocity. The x direction is 15 meters per second. We remember that the acceleration in the x direction is 0. And the other thing that we have are some vertical variables. So the vertical variables in the y direction, since this object is assumed to be on air and we're talking about neglect friction, is going to be negative 9.81 meters per second squared. The initial vertical velocity is 0 meters per second. Since it rolls off horizontally, initially there's no vertical motion of it. So initially it's going to be 0. There's also vertical distance, and that distance, there's a difference here, that is equal to 6 meters minus 3.6 meters. 6 minus 3.6 equals 2.4. So this change in vertical height is 2.4 meters. Something to note is when we're doing these types of problems where we have horizontal motion and vertical motion, you can't mix your variables together in the formula that we're going to pick. So we're solving for time. We have some initial speed in the y direction, in the x direction. We have our acceleration in the x and y direction, and we have a distance in the y direction. So let's bring up our reference table and let's see if we have any formulas that we can use. We could use this formula here, same formula that we used a while back. We could use this to solve for our time. So let's write that down. We have d equals VIT plus 1/2 AT squared. Now these are all y variables, so I'm just going to replace these. This is dy equals VIYT plus 1/2 AYT squared. Another thing to note is because our velocity is 0, this becomes 0. So we have dy equals 1/2 AYT squared. If I solve for t using some algebra, we're going to get t equals the square root of 2 times dy over ay. In class, this might have looked like 2h over g. Okay? That's what that might look like. So let's plug this into our calculator. So we're going to do the square root of 2 times the height difference, which is 2.4, and we're dividing by 9.81. And we get a time of approximately 0.70 seconds, which is choice 3. All right. Moving on. Last 2 multiple choice questions. 49 says 4 mechanical waves are created in the same medium over the same time interval. Which diagram represents the wave that transfers the greatest amount of energy? Greatest amount of energy for mechanical waves is going to be related to the amplitude. So we'll say that it's approximately equal to that. And for electromagnetic waves, what's related to the energy is the frequency. Okay, so we're looking for the one with the greatest amplitude, so that is going to be choice 2. For number 50, which diagram represents a light ray increasing in speed as it travels from one medium to another? So this has to do with refraction. Okay, so more bending away from the normal line means increasing speed. So we're looking, let's look at each choice here. So choice 1 has this angle as it comes in, and then it has this angle as it goes into medium A. That's a decrease in angle, so it's not choice 1. So we want, when I said more bending, I'm sorry, I was unclear. When I said more bending, it means increase in theta. So you can conclude that when you increase theta, you then increase the speed. Here's another case. The angle here decreases. This is the only example here where the angle increases. So we're going to use choice 3. We're going to use choice 3 here. Okay, so that wraps it up for the multiple choice questions. So now what I want to do is move on to the short answers. Okay, now when it comes to the short answers, your short answers, you have to show work for some of the questions. So this is the answer booklet from last year, and then when you guys take the Regents, there will be this answer book. So there's space to show your work, and then you'll notice here that for this, like for number 53, you don't have to put your unit in your answer. So you only have to put your units when you substitute. So let's see if we could go through these quickly so I can go to sleep. Okay. So for this, 51 to 52, that's this part right here. So 51 to 52 says, to charge a cell phone battery, 3.69 times 10 to the 3 coulombs of charge is moved through a potential difference of 3.7 volts. Calculate the maximum amount of electrical energy gained by the battery. Show all work, including equations and substitution. Okay. So let's write down my variables, okay? So we have charge, which equals 3.69 times 10 to the 3 coulombs. We have a potential difference, so voltage equals 3.70 volts. And calculate the maximum amount of electrical energy gained. So that would be W. For electricity, W is our energy variable. So this is the unknown. So let's open up the reference table. Page 4 in the reference table has this formula. Let's use a different color. Has this formula. That's what we want to use. So we're going to use V equals W over Q. We're going to cross multiply so that way we can get W equals V times Q. And then that's the formula that we're going to use to substitute. So W equals V, which is 3.70, times Q, which is 3.69, times 10 to the 3 coulombs. And actually, that's all you need to show in terms of the work to get full credit. The stuff that I have in red. But I'm going to continue. So this is in the calculator. It's going to be 3.7 times 3.69 times 10 to the 3. and we get 13,653. Okay, so that's a lot. And the units here, in case we forget that it's joules, we can multiply volts times coulombs. So volt coulombs would be the answer, which is equal to 13,653 joules. Now, realistically, what you should be doing is putting this in scientific notation. So in scientific notation, this would be 1.37 times 10 to the 4 joules. That's our answer. Okay. For number 53 says determine the magnitude of the weight of the, and just to clarify, this is where the points you would get. So this here would be 1 point for 51, and one of these answers here would be the other point for 52. 53 says determine the magnitude of the weight of the ice skater. And that's based on this problem here. So a 55 kilogram ice skater slides across, let's get rid of the calculator. A 55 kilogram ice skater slides across a level surface of ice, and the force of friction acting on the skates has a magnitude of 11 newtons. Determine the magnitude of the weight of the ice skater. So magnitude of the weight of the ice skater, weight is Fg times mg. And for this problem, you don't need to show any work since it's just 1 point. But the mass is 55 kilograms. And the weight, the acceleration due to gravity is 9.8 meters per second squared. And once we get this, that's 55 times 9.81 is approximately 10. So you get 550 newtons. Another acceptable answer is 540 newtons. Okay, so either one of those answers are acceptable. So if you put 9.81, you'll get 539 point something. And if you round it to 10, you'll get 550 approximately. All right, for 54 to 55, it says calculate the coefficient of friction between the ice skater and the ice. So coefficient of friction. This formula is on the last page of the reference table that has the coefficient of friction. There's only one formula on the reference table that has the coefficient of friction. It's this. So let's write that down. So we have friction equals coefficient times the normal force. Now, since this ice skater is on a level ice surface, that means that the normal force is equal and opposite to the weight. So we can replace, we can do that replacement like that, and then we rearrange this to solve for the coefficient of friction. Coefficient of friction is going to be friction divided by the weight. Our substitution is going to be 11 newtons. That's from the problem. 11 newtons is the force of friction. And the weight is from our previous problem. So my answer was 550. So I'll do 550 newtons. 550 newtons. And let's see what we get here when we calculate this. We get 0.02. No units because the units cancel out. So that's the answer for 55. So this right here is the point for 55, and this right here is the point for 51. Just this section part. Okay. Let's move on. So the next one says, base your answers to questions 56 and 57 on the information and diagram below and on your knowledge of physics. A student produces a wave in a flexible spring stretched along a tabletop by shaking one end of the spring at a frequency of 2.0 hertz. Determine the amplitude of the wave produced in the spring. So the amplitude of the wave produced in the spring here, if we have a line that kind of separates our positive and negative sections here, then this is our amplitude. And since the total measurement is 1 meter, half of that is our amplitude. So we get 0.5 meters. We don't need to put the unit since the unit is already here on our answer booklet. For 57, determine the wavelength of the wave produced in the spring. So for wavelength is going to be the total distance or length that we have divided by the number of let's say cycles. Okay, so total distance is 4.5. So 4.5 meters. And the number of cycles, we have 1 cycle. That's 1. We have 2. And we have 3. So that's 3 cycles. So we're going to divide by 3. So calculator, 4.5 divided by 3 is 1.5. So we'll put 1.5. Again, we don't need to put the units because we have the unit there on our answer booklet. Again, no work is needed to show 56 and 57. It can all be done in your calculator. 58. Scroll down to 58. 58 says 58 to 60 are together. So it says a 100 Newton box is pulled up a 20 meter long incline by a constant force of 80 newtons. The vertical height gained by the box is 10 meters. Determine the total work done in joules by the 80 Newton force pulling the box up to the top of the incline. So total work done in joules by the 80 Newton force. So we're talking about the force pulling it up to the top. So let's look at our reference table. Work is this formula right here. So work equals force times distance. So let's write that down. Work equals force times distance. Now, the force and the distance have to be parallel. That's a note. So force and displacement, we'll call it, have to be parallel. So if our force is this way, our distance that we're looking at is also this. So we're looking at that. So that happens to be pretty simple calculation. Work equals 80 newtons times 20 meters. 80 times 20 is 1600. So 1600 and Newton meters, but we can see that our units here are joules. So this is 1600 joules. So we'll put 1600 joules as our answer. For 59, determine the total amount of gravitational potential energy in joules gained by the box as it's pulled to the top of the incline. For gravitational potential energy is this formula. Gravitational potential energy is mg times delta H. Let's write that down. Gravitational potential energy equals mg times delta H. In this case, delta H is 10 meters. And mg is 100 newtons. So mg is 100 newtons. Delta H is 10 meters. This is 1,000 Newton meters or 1,000 joules. So we'll do 1,000 joules. Number 60 says, explain why there's a difference between the total work done by the 80 Newton force in pulling the box to the top of the incline and the amount of gravitational potential energy gained by the box as it was pulled to the top. So they're asking to explain why is there a difference between 1,600 joules and 1,000 joules. And you have various answers. You can say because of friction. You can say there's some kinetic energy. You can say there's some heat or thermal energy or internal energy or other energy present. Only pick one of these, okay? Don't include all three. You would only pick one if this was your answer. All right, next block of questions involve the circuit. The diagram below represents an electric circuit consisting of 110 ohm resistor and a 220 ohm resistor connected to a source of potential difference. Calculate the equivalent resistance of the circuit. Show all work, including equation and substitution. So for the 61 part, we're using the formula. Formula is going to be 1 over, actually, let's double check the formula. So this is a parallel circuit. So the formula that we need to use for equivalence resistance is right here. So we'll write down 1 over the equivalent resistance equals 1 over R1 plus 1 over R2. I'll stop at R2 since we only have 2 resistors. The next thing to do is to do a substitution. So 1 over R EQ equals 1 over 110 ohms units plus 1 over 220 ohms, remembering our units. So that right there is your point for 61. Okay, your substitution. Now, to continue this, let's put these in the calculator. So I'm just going to bring this work up here. 1 over REQ equals, so 1 over 100, let's put that in the calculator. 1 divided by 110 is 0.009 something something. And then we're going to divide 1 divided by 220. And that is 0.0045. Okay. So now what we're going to do is we're going to add those two together. So add the 0.00909, etc., etc. could have just put in the fractions, right? The alternative would be to do this. 1 divided by 110 plus 1 divided by 220. And what we get is 1 over our equivalence equals 0.013636, repeating. Okay? Oops. So, this is not the answer. So in order to get the answer, we actually have to take the inverse of that. So the inverse, if we bring back up our calculator, we're going to do 1 divided by this answer. So we'll put second minus sign, which gives us our answer, and that gives us 73.3. So our equivalence equals 73.3 ohms. The math involved to do that is you raise this side to the -1 and you raise this side to the -1. So you could put in parentheses 0.013636 repeating, and then you raise that to -1 and you get the same answer. Okay, so that's what you would do. All right, and this right here is your point for 62. For 63, 64, it says calculate the total current in the circuit. Total current in the circuit is going to be equal to this equation using Ohm's law. So let's write that down. Total current. Let's write down R equals V over I, and then we'll rearrange this to be I equals V over R. Now for total stuff, total quantities, we want to utilize the total voltage divided by the total resistance. So total voltage is the voltage of the circuit, which is 6 volts. So that's 6 volts. And the total resistance is what we calculated up here in the previous part. So 73.3 ohms. So 6 divided by 73.6. 73.3. So 6 divided by 73.3, that gives us 0.08185 ... amperes. Or if we forget that current is measured in amperes, you would say 0.082, we'll round that, volts per coulomb. So volts per ohm. This is also equivalent. Okay. For 65 says compare the power dissipated by the 110 ohm resistor to the power dissipated by the 220 ohm resistor. So for this one, again, we're going to bring up the reference table. Power dissipated is going to be here. Now we have a few options that we can think about. So we want to look for what variables we have. We have the resistance, we also have the voltage, and we have the current. So what we can say is, let's hide this for a second. So we have the 110 ohm resistor and the 220 ohm resistor. So we need to use one of these formulas that has the resistance in it. So it can either be this one or this one. I think it would be easier to use this one, because the reason for the parallel circuits have the voltage all equaling the same. So if we look at that relationship, so power equals V squared over R. Since it's the same voltage across the whole thing, so for the first resistor, it's going to be 6 squared divided by 110 ohms. And then for the second resistor, it's going to be 6 squared divided by 220. And according to this, we can say that the power dissipated, did I spell that right? Dissipated by the 110 ohm resistor is greater than the 220. Okay, because 36 divided by 110 is greater than 36 divided by 220. All right, moving on. Part C, this is the last part of the Regents. It says, for 66 through 70, a group of students constructs a catapult that launches a ball at a target placed on a lab bench. Students measure 0.80 seconds from the time the ball is released until it strikes the target, located a horizontal distance of 2 meters from the release point. The ball reaches a maximum height of point P, which is 0.78 meters above the ball's release point. The target is at the same height as the release point. Neglect friction. 66 to 67 says calculate the horizontal component of the ball's initial velocity. So, horizontal component. If we want to calculate the horizontal component of the ball's velocity, that formula we can use is distance over time. So we can use this since there's no acceleration in the x direction. So distance, horizontal distance, is 2 meters. And time is the total time, which is 0.80 seconds. 0.80 seconds. So this is 2 divided by 0.80, and you get 2.5 meters per second. So that's number 66 and 67. For calculate the vertical component of the ball's initial velocity for the vertical components. So we need to figure out the vertical component. That's unknown. We know that at the peak here, the velocity in the y direction is 0. So we can say 0 there. We can also say that the acceleration in the y direction is 9.81 meters per second squared, and we know the distance in the y direction at that point is 0.78 meters. Only thing missing here is time. So we actually don't need the time, however, because we can use the formula from the reference table, which is this formula. This is found on page 6. Okay, so we can use that. So let's see. So VFY is 0, so we can get rid of that. VIY is what we're solving for. 2 is just a coefficient, we'll just bring that down. A is 9.81, and D is 0.78 meters. So in this case, we want to make sure that we substitute negative here, because if not, we're going to run into some issues. So let's simplify this. We got 0 equals vi squared. And then according to the calculator, we have 2 times 9.8 times 0.78. And that gives you negative 15.288. And then we're going to bring this over to the other side. So this is 15.288 equals vi squared. And then we take the square root on both sides. So that's the square root of that answer. And we get 3.9 meters per second equals vi. Alright, so that's 69. Next question. On your answer booklet, draw an arrow originating at point P that represents the direction of the ball's acceleration at point P. So acceleration at point P is downward. This is the acceleration due to gravity. There's no acceleration in the x direction. There's only acceleration in the y direction. Okay. This next block of questions, 71 to 75, deals with springs. It says a spring with a spring constant of 2,600 newtons per meter is compressed 0.10 meters from its unstretched position. The spring is released, propelling a 3 kilogram block along a horizontal frictionless surface. The block is then, it collides with a stationary 1 kilogram block. The block remains joined and they move together as shown in the diagram below. So to go over what just happened, or what was just read. Spring is compressed initially. Then what happens, it's released. This calculator's in the way. So spring is compressed, then it's released. That energy is converted. This is what it looks like before the collision, this 3 kilogram block. Then it collides with the 1 kilogram block. They both stick together and they move together. So this is a key term, move together, indicating this is an inelastic collision. So let's go to question 71. Question 71 says, determine the total amount of elastic potential energy stored in the spring when the spring is compressed. So elastic potential energy, which is right here, elastic potential energy is 1/2 kx squared. So let's write that down. Elastic potential energy is 1/2 kx squared. So K, it was mentioned, K is 2,600 newtons per meter. So we'll plug in 1/2 2,600 newtons per meter, and x is going to be 0.10 meters. That term is squared. So let's put that in the calculator. 1/2, that's 0.5, times 2,600 times 0.10 squared. That gives me 13. Answer is 13 joules, and that's what I'll put in to my answer key here. Now let me just show something here on the calculator. If I put 1 divided by 2, and then I multiply by 2,600, and then I multiply by 0.10 squared, I still get the same answer. Okay, so sometimes you can get away with not using parentheses. Sometimes you can get away with using decimals or fractions. Just be careful. I would err on the side of caution and use parentheses or decimals instead of fractions. All right. Next question. It says, assuming all of the spring's energy is transferred to the 3 kilogram block, calculate the speed V1 of the 3 kilogram block immediately after it is propelled by the spring. So this is saying that all of the potential energy of the spring converts to kinetic energy. So on the reference table, kinetic energy is this formula. Kinetic energy equals 1/2 mv squared. Okay, so potential energy of a spring equals 1/2 mv squared. That's this before and after. So now what we're going to do is we need to solve for v, since the question asks to determine the speed. So we're going to solve for v. I'm going to do the algebra really quickly. So this is going to be 2 times the potential energy equals mv squared. Then it's going to be 2 times the potential energy over m equals the velocity squared. And then finally, it's going to be the velocity equals the square root of 2 times the potential energy over the mass. This is the formula we're going to use. We're going to substitute 2 times the potential energy. The potential energy was from the previous problem, 13 joules. And the mass is 3 kilograms. So calculator, we're going to do square root of 2 times 13 divided by 3. And we get V equals 2.94 meters per second. Let me just verify if that is correct. Yeah. Cool. Okay. So next it says calculate the speed of V2 of the 2 blocks after the collision. So going back to this diagram, there is a collision that occurs where the 3 kilogram block collides with the 1 kilogram block. So this is a situation of momentum. The initial momentum equals the final momentum. The initial momentum is going to be the mass of that first object times the velocity of the first object. It's just one object. And then it's going to be equal to the mass of the first object plus the mass of the second object times this new speed. Okay? So this is the before, this is the after. This is the before, this is the after. Before, after. So let's write this down in our answer book. So initial momentum equals final momentum. The first object times the first velocity. And if we want to be thorough, it's going to be the second object times its velocity, but that's 0. It's at rest. And this is going to be equal to first object plus the second object times the new velocity. So we need to solve for that variable there. So since this equals 0, we have m1 v1 equals m1 plus m2 in parentheses times v2. We can divide by m1 plus m2. Okay, this cancels out. And we divide by m1 plus m2. And we'll get an answer, we'll get a formula of v2 equals m1 v1 over m1 plus m2. So let's bring this up here. Let's see what that substitution looks like. m1 times v1, so M1 is 3 kilograms. V1, which is this right here, so 2.94 meters per second, over M1 plus M2, that's 3 plus 1, that's 4 kilograms. So let's put this in a calculator. 3 times 2.94 divided by 4 equals 2.2. So V2 equals 2.2 meters per second. And this makes sense. Initially it was moving at 2.9 meters per second. It hits something and it slows down to 2.2. Great. All right. These are the last questions. 76 says, a mercury atom emits a photon when an electron in the atom moves from energy level F to energy level D. F to D. So initial energy is F. Let me write this down actually over here. Initial energy is F and final energy is D. So let's bring up the reference table, and this is page 3. For mercury, we have F, which is this value, and for D, we have this value. So F is negative 2.68 electron volts, and for D it's negative 4.95 electron volts. This formula that we need to use is on page 5. It's this one, the energy of a photon. Energy of a photon equals the initial minus the final. So we're going to put that into our calculator. That is, the initial is negative 2.68 minus negative 4.95. Now we get answer 2.27 electron volts. Number 77 says, determine the energy of the emitted photon in joules. So to convert electron volts to joules, there's a conversion factor on page 1 of your reference table. Electron volts to joules is right here. Electron volts to joules. So we have 1 electron volts equals 1.60 times 10 to the negative 19 joules. So if we have 2.27 electron volts, that is going to be 2.27 times 1.6 times 10 to the negative 19. And we're going to write down 3.63 times 10 to the negative 19 joules. Cool. Number 78 to 79, calculate the frequency of the emitted photon. Frequency of the emitted photon. We'll need a few things here. So page 5, energy of a photon equals Planck's constant times frequency. Planck's constant is on page 1 of the reference table. Planck's constant is right here. That's 6.63 times 10 to the negative 34 joule seconds. Frequency is what we're solving for, and the energy of the photon is what we just got from number 77. So that's 3.63 times 10 to the negative 19 joules. This gives us frequency equals, and we're going to use the calculator here. Frequency equals 3.63 times 10 to the negative 19 joules divided by 6.63 times 10 to the negative 34 joule seconds. And so that gives us 3.63 times 10 to the negative 19 divided by 6.63 times 10 to the negative 34. Here we get 5.48 times 10 to the 14 hertz is what the unit of measurement for frequency is. Okay. Last question. Last question says, based on your calculated value of the frequency of the emitted photon, determine the classification in the electromagnetic spectrum. So if our frequency is 5.48 times 10 to the 14, we need to check on the electromagnetic spectrum what that equals. So 5.48 times 10 to the 14 hertz. 10 to the 14 hertz is visible light. So we're looking for 5.4, which ends up being somewhere here. So green light is what we think it might be. So what we'll put down on number 80 is visible light or green. So that's the type of photon it is. Okay, 3 hours later, we finished the Regents. So we actually just finished on time. So hope you guys enjoyed this. If you guys have any questions, you could reach out to me. I'm gonna end the stream and then you can either comment questions or message me.